let's talk about how to hurt these models. So the first thing I tried was poisoning. We've been training a classification model to classify numbers. We had the correct number and the predicted number. So what I did was just change the labels. That's an easy way to poison it. So you got your training and test set is here. I have about 200 of each of the digits in the training set and about 100 in the test set. So I now poison 10 of the ones. I take 10 of the one labels and turn them into twos. So now I'm lying to the model with the wrong label, and the end result is I trained from the poison data, and the end result is I have no effect at all on the amount of correct or incorrect ones. Let me go back here. The previous model had this result. The ones were correct was 1. So here's, before and after. So in the 220, I had 220 ones and went down to 210. I had 198 twos and went up to 208 twos. I took 10 of the ones and relabeled them as twos. And now that I'm done, the ones have only 2 incorrect and the twos have 11 incorrect. And the previous model was just the same. I'll find the error. The previous model, the ones had 2 incorrect and twos had 12 incorrect. So poisoning 10 of the inputs had no effect at all. So I poisoned 30 of them out of 200, and then it had the tiniest effect on the output. Now I got 13 errors in the 2 instead of 12. So changing the labels had a surprisingly small effect here. So this is a kind of dumb version of poisoning. If you poison 100 of them, then you start making half of them the wrong label, then it starts really hurting it. But anyway, I was surprised how ineffective putting in bad labels was. So we're going to have to find a better poisoning method. Let's just go on to the next one. All right, so this is, let's go down to poisoning labels with SecML. There's a security machine learning library in Python, SecML, just to do this sort of attack. And what this is going to do is after you've trained a machine learning model, remember it treats each pixel independently. So when it tells a 1 from a 2, there are certain pixels it's choosing to make that distinction, which are not what a human would choose, because it's not finding the lines and the edges the way a human would. So it looks at the machine learning weights and it figures out which pixels matter most to you. I'm going to change those values to poison the model. So it will carefully calculate a poison model. Now here's a simple example with separating dots. I have blue and red dots. I train a model to separate the blue from the red. Okay, so I got a model here that's working. And now I want to move one of these dots, and I want to choose a dot that's going to have the most effect. Or I want to find out what motion would have the most effect. So I take one dot, and I run it through the SecML model, and it will move that one dot. It's going to appear as a star someplace. Having trouble finding it. Chart on the left shows the original data. The chart on the right shows the poison data. One red dot, removed one red dot. It took one red dot in the top and labeled it blue. That's what it did. And that has some effect on the poison model, but not much. It took its accuracy to 24%. And now this is again manipulating labels. And as before, you have to change a lot of labels before you poison it very much. And there's various things to try there. But let's move into the more fun one, which is poisoning by gradients. So this one, you train a model. We got a data set of these dots again. We train the model, and now we can visualize the results, and you can figure out how sensitive it is to these areas. This is like a heat map. What regions of the model have the most effect on the parameters, and what regions don't? And so you want the red areas where you have the attacker, objective, and gradients. And so if you can move things into the high areas, you'll have more effect. And I think this one I have a diagram showing you here. Sorry, I have a little trouble finding the fun graph that shows, the stars are the altered images. There. Yes, so this blue dot, I moved a dot over to here and colored it blue. And that had a big effect on this portion of the model, as you can imagine. And here, I poisoned more points. I poisoned the first 20 dots. And so all these stars are poison points. I put a bunch of red ones down here, and I put a bunch of blue ones over there. And now you can see it's really starting to confuse the model. So you can have carefully chosen changes that will really confuse the model. And for the most fun, we can poison visible images. This is the one that's easiest for a human to intuitively understand. So you use the same SecML library. You train a model to do the 10-way classifier, although I think in this case we settle on just 5s and 9s, a 2-way classifier. We're telling 5s from 9s, so here's the original data and the original labels. Now we train a classifier, and here it is getting them right. The predictions in parentheses, so 9 is a 9, 5 is a 5, 9 is a 9. So it's 100% successful on the first few images here. Now we do a poison attack, and there are some parameters where we choose how much we're going to modify the image. And the poisoned images, this is classifying test images. And here we are poisoning 5 images. And I wanted to see the poisoned images with the snow in them. Yeah, here we are. It put this little dot here, and it put this little gap here. And we go down here. This is what the poisoning looks like, just a few little dots. And it has a strong effect on the classification. It's not as clear as I wanted to see here, but we'll see it in a future one. Let me just race ahead to the next one here. All right, let's get rid of this nonsense. All right, let's start with deep neural rejection. Oh, that's poisoning. Okay, I'm sorry. Now I remember what's going on. The poisoning attacks are all relatively ineffective. So let me point out something. In these simple test cases I've shown you, the poisoning attacks have not been impressive, but in reality, they're incredibly powerful. There was a test done about a month ago where they wanted to train a large language model to give people medical advice. And so they trained it on like medical textbooks, real authoritative medical data. And then they tried to see how much false data can we add to the data set, how much will that have an effect on the output? And they found that even putting in a very small amount of false data, like 1%, was enough to make the output give the patient the wrong answer something like 10 or 15% of the time. So this is extremely concerning if you consider that all the current large language models are trained on just random crap from the internet. A lot of that data is bad, a lot more than 1%. So in the large language models, they're much more sensitive than these. Now, let me stop this one and make a different video, the next one.